In the last video, I introduced the notion of a power series working off of one main example. What we're going to do in this lesson is look at a few more examples of power series. For each, we will identify the coefficients of the power series, the center of the power series, and then what values of the independent variable x cause the power series to converge. So we'll find the domain of convergence, which we will often call the interval of convergence. Let me just revisit this general notation here, and then we'll look at a specific example before moving on to maybe some more interesting new examples. For this notation at the top, we are indexing from n equals 0 to infinity expressions where we are basically constructing a function of x. The first value of n is n equals 0. So I plug that in, I get c sub 0. That's the first coefficient times the quantity x minus a to the 0, but I won't write that because that's the number 1. Then if we plug in n equals 1, we get another coefficient. So c sub 1 is just a coefficient, it's a number, times the quantity x minus a to the 1 power. Continuing on, when n equals 2, we get c sub 2 x minus a squared, and then c sub 3 x minus a cubed, etc. What we talked about in the last lesson was that if you look at any partial sum, so if I take this partial sum that consists of the first 3 terms, it's a polynomial. In this case, it's a quadratic polynomial. These numbers, c sub 0, c sub 1, c sub 2, just to reiterate, these are coefficients. So let me just point that out. Whereas this number minus a here is telling us that the center is a. Often the center is 0. In fact, after this warm-up example, the 3 remaining examples in this lesson will all be centered at 0. What you don't want to do with this expression is take this and multiply out, like you don't want to do x minus a squared and then square that out. You want to leave it in this form. Let's look at an example where we have this kind of non-zero center here. So consider the power series going from n equals 0 to infinity of terms which look like x minus 1 to the nth power. If I start to write this out, my first term is going to be the number 1. So 1 times x minus 1 to the 0 plus x minus 1 plus x minus 1 squared plus x minus 1 cubed, like that. In this particular example, the coefficients are all 1. And the center is the number 1. So the coefficients and the center are 2 values that you can typically read right off of the general power series expression. What we want to focus on in this lesson is determining what values of x cause this power series to converge. Okay, I'm going to do one particular approach on this power series that I will then shift away from for the remaining examples in this video. In fact, there are 3 more examples after this one in this video, and I call them examples 1, 2, and 3. So let's think of this as our warm-up example, or maybe I should have labeled it like example 0. This is a lot like the example that we looked at in the previous video, except that I've shifted the power series over to have a center of 1, whereas the example that we worked through last time had a center of 0. So let's pick up with the approach we had then, where we said that this looks like a geometric series where the base is the quantity x minus 1. So recall a geoseries of the form n equals 0 to infinity r to the n, where here we can imagine that the base r is a number, like 1/2, converges when the absolute value of r is less than 1. It diverges otherwise. In this example, what we're going to do is think of x minus 1 as that base. So for what values of x can we say that x minus 1 is less than 1? So we get convergence when the absolute value of x minus 1 is less than 1. So here, this x minus 1 expression is analogous to the space R for our more traditional looking geometric series. Okay, what you can do with this inequality is what I think of as like unfolding it or expanding it. If the absolute value of x minus 1 is less than 1, that means that negative 1, so negative, this number, negative 1 is less than x minus 1 is less than 1. So that's how you can convert this absolute value expression to like a chain of inequalities. I want to give a statement about x. So let's add 1 to all three parts of this inequality here. So we'll get 0 is less than x is less than 2. Okay, let me pause there for a second, just let you kind of work through that. Okay, so this defines what we can think of as an interval of convergence. It's the open interval from 0 to 2. Those are the only values of x that will cause this series, which has the form of a geometric series, to converge, because it's going to converge exactly when a geometric series converges. However, I would like for you to get in the habit of taking a minute and analyzing the endpoints of the interval of convergence. So what happens when x equals 0, and what happens when x equals 2? It's possible for a power series to start with this kind of interval of convergence, and you actually pick up convergence at either endpoint. So again, it's just a good habit to have whenever you are analyzing the interval of convergence for a power series. Well, when x equals 0, we have negative 1 to the n. That's going to give us 1 minus 1 plus 1 minus 1 plus 1. That doesn't converge. The sequence of partial sums doesn't converge. If I plug in x equals 2, then we would have 1 to the n. So that's going to look like 1 plus 1 plus 1 plus 1 plus 1. That does not converge. So this is the interval of convergence. It's the open interval from 0 to 2. Notice that the center of this interval, the midpoint, is the center 1. So that's one observation to kind of keep in mind as we work through the next few examples. So let me leave this example where it is. I wanted to start with this example because it looks a lot like the example that we worked on in the previous video, just shifted one unit over on the x-axis to shift from x equals 0 to equals 1. Everything else is the same. So our interval of convergence shifted over by 1 as well, so that we're looking at a domain of convergence from 0 to 2, that open interval. The plan for the rest of this video is to work through 3 new examples. So they're not going to look necessarily like this. We're going to have 3 new power series, and I would like to show you how to figure out what values of x cause convergence for each of those power series. So I'm going to introduce in 3 new power series. For each, we'll start by just identifying these key pieces of information. So we'll say, what are the coefficients? What's the center? But then what we really want to focus on is figuring out what the interval of convergence or domain of convergence for each of the examples is. The 3 examples are going to have 3 different looking intervals of convergence. But it turns out that we can take those 3 behaviors and summarize them to say that, hey, all power series are actually going to behave like one of these 3. So we'll do 3 examples, and then we will kind of summarize. The video after this one is going to work through 3 more examples. So just do several examples of power series until you get to kind of a routine way of analyzing the domain of convergence for your power series. Okay, let's look at this example of a power series we haven't seen before. So for the power series whose terms look like n factorial x to the n, let's identify the coefficients and the center, and then we will work out for what values of x does this power series converge. So it might be helpful to start by just expanding the power series for a few terms to see what it looks like. If I start with n equals 0, natural place to start. If I plug in 0 factorial is 1, x to the 0 is 1. So the first term in my power series is the constant 1. Then the next term is 1 factorial times x, so that's just going to be 1x. Then after that, we get 2 factorial times x, which is, 2 factorial times x squared, so that's 2x squared. Then 3 factorial is 6. I'm actually going to write it as 3 factorial. So 3 factorial x cubed. Likewise, let's write 4 factorial x to the 4th, etc. Okay, so that's the start of what this power series looks like. What are the coefficients here? The coefficients are 1, 1, 2, 3 factorial, 4 factorial. In general, for each choice of n, they are n factorial. So the coefficients are these n factorial numbers. And then for the center, notice there's no shift here. It's not x minus anything. It's just plain old x. So our center is at 0, as is often the case. So we are centered at 0 on the number line. Next thing we want to do is work out what values of x, when plugged into this expression, give you a convergent series of numbers. Now, all power series always converge at their centers. So if I plug in x equals 0, I'm going to get a convergent series. In fact, it's quite easy to work out what it would add up to, because if I plug in x equals 0, everything starting here and on is just 0. So when x equals 0, our series adds up to this leading number 1. Are there any other values of x that would provide convergence? What I recommend doing here is the ratio test. So let's work through the ratio test, and I think I'll do the computation and then kind of explain why it was helpful. So for the ratio test, what we're going to do is take the limit as n goes to infinity of the absolute value of the ratio of the form of the n plus 1th term in our series expansion to the nth term. So what that's going to look like for this power series is the n plus 1th term is going to look like n plus 1 factorial x to the n plus 1. Divide that by the form of the nth term, which is n factorial x to the n. Okay, so let's simplify this. Factorial, you always look for a way to simplify that when you're doing the ratio test. So in particular, what I'm going to do is take that expression in the numerator and write that as n plus 1 times n factorial. Because if you start to expand this, it's going to look like n plus 1 times n minus 1 times n minus 2. But everything after that first term can be summarized as just n factorial. So n plus 1 times n factorial. And then x to the n plus 1 is going to divide out with the x to the n. How about I just write that for this first example as x to the n times x. Okay, maybe this is unnecessary. So that's a choice I've made there, kind of a stylistic choice, if you will. Divide that by n factorial x to the n. Okay, with ratio tests, we usually get some nice cancellation, and we see that here with the n factorials canceling out along with the x to the n's. Okay, what's going to happen here is we are taking an absolute value. The number n starts at 0 and increases to infinity, so this n plus 1 expression is always positive. However, x is a mysterious value. We don't yet know for what x values this power series converges. So when I have x here, I don't want to assume that it's positive or anything like that. So what I'm going to do is rewrite this one more time as the limit as n goes to infinity of the positive number n plus 1 times the absolute value of x. Okay, so that's what I wanted to do with those absolute values is just put them around the x. The thing about the ratio test is that the ratio test gives us convergence whenever, it gives us absolute convergence if this number is less than 1. It's inconclusive if this ratio works out to be 1, but it's divergent if this number is greater than 1. So here's what we want to observe at this moment. Is if I choose any value of x, which is not 0, we already know we converge when x equals 0. So imagine I pick any other possible number of x, plug it into this expression. X is now a fixed number. Plug in x, take its absolute value. This is just a fixed number. Let n go to infinity. This is a fixed number times something which is growing arbitrarily large. This is going to grow to infinity if x is anything other than 0. So what you could do is write that this limit has two possibilities. It goes to infinity. Actually, I'm just going to write an arrow to say where it trends. It trends to infinity if x is any non-zero number. However, if x is 0, then when I plug 0 in for this x expression here, I literally have 0. So it's n plus 1 times 0. That's always 0. As n goes to infinity, it stays at 0. So it's 0 if x equals 0. If we compare this to the statement of the ratio test, what we are now saying is, hey, it converges when x equals 0. It does not converge at all. It diverges when x is not 0. So this power series only converges when x equals 0. Sometimes you are asked to provide the domain of convergence as an interval. In this situation, we are only converging at a single point. So perhaps the most natural way to express that as an interval is to just give it as a single element set consisting of one number, just the number 0. In this example, we are looking at a power series whose terms have the form x to the n divided by n factorial. So again, if we start to write this out, when n equals 0, x to the 0 is 1, divided by 0 factorial. 0 factorial is 1, so 1 over 1 is 1. Okay, that's the first term in our power series expansion. When n equals 1, we get x over 1, so x over 1 factorial. Then x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, etc. This is similar to the previous example. We have similar expressions here. Our coefficients are the reciprocal of example 1. So the coefficients are 1 over n factorial in this case, but the center is still at a equals 0. Okay, what I would like to do now is the ratio test in order to determine for what values of x this power series converges. This is very similar to the previous example in that we have, x to the n, we have an n factorial expression. So let me give you a minute to go ahead and set up the ratio test, just like we just did a second ago with example 1. Take it as far as you can, maybe all the way to the conclusion, and then I will finish the exercise. Okay, here's how I would set up the ratio test. So let's write the limit as n goes to infinity of the absolute value of the n plus 1th term. What I'm going to do is write x to the n plus 1 divided by n plus 1 factorial. And then to divide by the nth term is to multiply by its reciprocal. So let me write times n factorial divided by x to the n. And by the way, if you're rusty on the ratio test, it might be a good idea to go back and revisit the lesson that we did on the ratio test so that you can kind of remind yourself of how this computation works. Even though we have an x term here, and we didn't before when we first learned the ratio tests, kind of the mechanics of working through this limit are very similar. Okay, we have very similar computations to what we had in example 1. In particular, n plus 1 factorial is n plus 1 times n factorial. So we'll see the same sort of cancellation that we just did a minute ago. So this is n plus 1 times, n plus 1 times n factorial. Okay, there we go. So overall, this becomes the limit as n goes to infinity of x to the n plus 1 divided by x to the n just leaves us with x. And then the n factorials are going to cancel, leaving us with n plus 1 in the denominator, like that. Now, just to emphasize that x could be any real number, we're testing all possible values of x. N plus 1 is positive. Let me rewrite this limit one more time. I'm simplifying this absolute value construction so that it looks like the absolute value of x divided by the positive number n plus 1. Okay. What happens here is that if we pick any value of x, any value at all, and plug it into this numerator, this is just a fixed number. Even if x is really large, it's a fixed number. N is what's going to infinity. X is fixed, n is going to infinity. So this is a number divided by something growing arbitrarily large. So this limit is 0 for all possible values of x. So what this means is that this power series converges for every single choice of x. No matter what, when we plug any choice of x into the ratio test, we get a series which is absolutely convergent. So this number being less than 1 tells us it's absolutely convergent, so it's convergent. That's true for all possible values of x. That means that the interval of convergence for this example is the whole real number line. So we have convergence from negative infinity to infinity for all values of x. Okay, this is our last example before I summarize the different types of behavior that we observe when we're looking for what values of x cause a power series to converge. So in this example, it's a little bit of a strange looking power series. Let me expand out the first few terms. If I plug in n equals 0, we have x divided by 2 to the 0th power, that's 1. If I plug in n equals 1, we have x over 2 to the second power. I'm going to write that as x squared over 4. Then if I plug in n equals 2, so this was n equals 0, n equals 1, n equals 2 is going to give us x to the 4th over 16, etc. This is going to ultimately be fine to work with this, where we just see the even powers. But if I want to compare with the types of power series expressions that we've been working with, let me drop in the terms that we're missing. So what do I mean by that? Well, we have, let me try to color code this. Okay, we had a 1, and then we had 0 times x, and we had x squared over 4, and then we have 0x cubed, then we have uh, x to the 4th over 16. The idea here being that this looks like the form that we've been seeing, which is the sum from n equals 0 to infinity of c to the n, x minus 0 to the n. In other words, the center here, as it has been for all the other examples that we've had, examples 1, 2, and 3, the center is at n equals 0. Okay, that opening example, that wasn't true. The center was shifted, but here the center is 0. Written in this way, we can describe the coefficient Cn as basically one of two choices. So for this series, this form of the series, we would say the coefficients are 1 over 2 to the n. Is that right? 2, this is 2 squared, 3, 2 to the, yeah, that's right. Sorry, needed a moment to check my math there. This is when n is even. And 0 if n is odd. So the coefficients that I just wrote down here are based on this kind of strict interpretation of the form of a power series. However, we will see power series examples where we're just looking at, say, the even powers of the independent variable or the odd powers of the independent variable. And actually, if we're just interested in determining for what values of x those power series converge, we don't need to go through this process of kind of manually inserting what feel like the missing terms. Instead, we can work with, say, this expression here and do the ratio test on that, and that will be sufficient. So if you look at this x over 2 to the 2n power, one approach would actually be to treat that like a geometric series like we did in the kind of opening example 0. I'm going to stick with the theme of the last two examples and use the ratio test on this expression. So let me see what we can do here. Why don't I take a second to erase all of this? So now that we went through this work of kind of reinterpreting this power series in the traditional form to identify the coefficients, we don't need them in order to work out the x values that cause this power series to converge. So let's get rid of this, and then we'll come back in a minute and finish the problem by figuring out the interval of convergence for this power series. Okay, now that we have more room to finish the problem, let's determine the interval of convergence for this power series. As I mentioned, you could take a geometric series approach to working that out, just like we did for that opening warm-up example on the first slide, but I'm going to do a ratio test again. So here's what that will look like for this particular power series. can set up the limit as n goes to infinity of the ratio of the n plus 1th term to the nth term, I'm going to go ahead and take this fraction raised to a power and do the numerator to the power, denominator to the power. So x over 2 to the 2n is the same thing, or rather 2 times n plus 1, because we're going to do the n plus 1th term. That's the same thing as x to the 2n plus 2 divided by 2 to the 2n plus 2. Okay, so this whole expression is x over 2 to the 2 times the quantity n plus 1. Okay, so this is the n plus 1th term. To divide that by the nth term is to multiply by the reciprocal. Again, kind of breaking it up into individual powers of the numerator and denominator. After I take the reciprocal, that's going to look like 2 to the 2n divided by x to the 2n, like that. Okay, so this was the n plus 1th term. And this is the 1 over the nth term. Okay, I don't know if, if you can read this teeny tiny handwriting, but just trying to talk through how I set up this ratio. Okay, let's do some cancellations. We have x to the 2n dividing into x to the 2n plus 2. That's going to get rid of that leading 2n term. Similarly, 2 to the 2n is going to get rid of the 2n part of this exponent down here in the denominator, leaving us with the limit as n goes to infinity of x squared divided by 2 squared, 4. Notice that the independence is all canceled out. There's nothing here left that has an n in it. So there is no n to let go to infinity here. This limit is just x squared over 4. What does the ratio test tell us? We have absolute convergence if this is less than 1. We have divergence if this is greater than 1. And then it's inconclusive if this is 1. So what we will do is set it less than 1 to get the overall interval of convergence. And then we will test the values that would give us a ratio of 1, because we know that if it's greater than 1, then we diverge. Okay, so this is less than 1 when x squared is less than 4. So that tells us that our initial domain of convergence is between -2 and 2. We're not done. I want to step back for a second, but we have to keep going with this a little bit further. When you do the ratio test and you set the result less than 1, it gives you, in this case, this nice like domain of values for x between -2 and 2. If x were either 2 or -2, when I plug it into here, I get a ratio of 1, inconclusive. And if x is to the left of -2, so if x is more negative or if it's greater than 2, we get divergence. So that means that we need to test -2 and 2 manually, because these are the two values for which the ratio test is inconclusive. So we will manually check these, knowing that we have convergence between them. Okay, can I do this on this board? Probably. Okay. Let's check -2 and 2 both individually. What that means is literally just take them and plug them into the series. It produces a series of numbers and then figure out if that series of numbers converges. So check x equals -2. When we put in x equals -2, we get -2 divided by 2 to the 2n. Well, that's -1 raised to even powers. Every exponent here on this -1 is even. So if I actually wrote out this series, I would get 1 plus 1 plus 1 plus etc. So this diverges. Similarly, if I check x equals 2, we plug in x equals 2, just literally plug it into the series and see what you get. We get 2 over 2 raised to the 2n. Looks the same over here as what we just did. This is 1 raised to the 2n. You start expanding that, that's going to be 1 plus 1 plus 1 plus etc. This also diverges. So it turns out that this endpoint behavior, what happens at -2 and 2, could not be deduced directly from the ratio test because that's the inconclusive situation, but we can literally check it. We checked it manually. We got that it diverged for both. So the interval of convergence is actually this interval from -2 to 2. If you write that as an interval, use parentheses to indicate that the endpoints -2 and 2 are not included. Okay, so this is our interval of convergence for this particular power series. In examples 1, 2, and 3, we provided the interval of convergence for 3 different power series. The result was different for each one. However, it turns out that the 3 behaviors that we saw are the only 3 behaviors that you can possibly see with the power series. So what I'm going to do now is break these into 3 cases. Each case here matches the example. So case 1, we'll go with example 1, example 2, example 3. For the what I called example 1, we had that example 0. So I'm referring here to that in factorial x to the n example that we saw with example 1. We said that that power series only converged at its center, which for that example was x equals 0. For the general notation, that's would be when x equals a. So the first possibility for a power series is that it only converges at the center. So you can see that. Every power series converges at its center, and some of them will only converge at the center. The next example, where we had terms that look like x to the n divided by n factorial, we worked out through the ratio test that that power series converged for all possible values of x. In other words, the interval of convergence was from -infinity to infinity. So you can see that. Okay, so those are 2 possible behaviors that you can see only at the center, or kind of the reverse, like every possible value of x. Both the warm-up example, example 0, and example 3 had what felt more like proper intervals as the domains of convergence. And that is case 3. So what I'm going to do is say that there exists a number capital R. And for this case 3 situation, let me make precise here that it's a positive finite number, capital R, so that we definitely get convergence when x is within distance r of the center. So how I'm going to phrase that is so that all x satisfying that the distance from x to the center is less than r calls convergence. While all x whose distance is greater than r calls divergence. So all x satisfying that the distance from x to a, so the absolute value of x minus a is the distance from x to a. If that distance is greater than r, we get divergence. I've left out the possibility here that the distance from x to a is exactly r. That's the situation that we just saw in the previous example where the ratio test is inconclusive and we check it manually. So let's see if I can squeeze it down here. The 2 values of x equals a plus or minus r, must be checked manually. And the last example, neither of them converge, but it's possible that one of the two will cause convergence or maybe both cause convergence. You just check them manually. So let me write out the possible intervals of convergence that you could get for this third case. Here it's easy. It's just a single point and the whole real line. Here, the possible intervals may look like what we just saw was an example of a minus r through a plus r with parentheses, meaning that the endpoints did not cause convergence. So this is an open interval. Or it could be like the left one was okay, so I do square bracket to say that this causes convergence, but this one doesn't. Or it could be the reverse. Or it could be both. Like that. Okay. All right, let me pause for a second here just to let you digest these three cases, but I want to say a little bit more about this number r, and I also want to link it to the first two cases, and maybe you do too. So looking at these first two cases, could you try to apply this notion of an r value to cases 1 and 2? Let's make a few more remarks about this number r. R is called the radius of convergence. You can think of it like the radius around the center A. So we call this the radius of convergence. And in this third case, it feels very natural to measure this number r, kind of defining how far away from the center we're allowed to be. But it extends naturally to the first two cases. Case 1 is like saying you can't leave the center. So this is r equals 0. Whereas the second case is like saying r is infinity. I don't usually like to write that something equals infinity because infinity is not a number, but that's okay for the second case for power series. So our three possible types of convergence that we look for when we're analyzing the domain of convergence for a given power series, it really comes down to determining this radius of convergence. Is it 0? Is it infinite? Or is it a finite positive number? We often are more interested in the radius of convergence than the specific interval of convergence. So I might not ask you for, say, all this endpoint analysis to figure out exactly the shape of the interval of convergence for this third example, but what we almost always want to work out is the radius of convergence. So that's going to wrap up this lecture. But if you're like, wait, I'm not ready for this, our next video is just three more examples, just working out this radius of convergence. So we will do some more ratio test computations on some power series and try to figure out what the radius of convergence is for this power series so that we can classify which of these three cases we're in.